All right, we are back to look at section 4.6 notes, where we're going to talk about polynomial and rational inequalities. That's the objective, is to solve those polynomial and rational inequalities. Quick review. What are the main differences between solving equations and solving inequalities? So equations have single solution values like x equals 2 and x equals 7. They'll have a list of set solution values. So the solutions are things like x equals some number and maybe x equals another number. And there might be a couple different things, right? But when I solve an inequality, our solutions are going to be intervals. All right, so topic 1, polynomial inequalities. We've had some experience solving linear inequalities, but more complicated polynomial and rational functions require more. We're going to treat the inequalities as if they are equations, and then we're going to test the intervals, the values between the zeros, which are either less than, greater than, whatever it needs to be, in order to find the solution sets. So we're going to have solve and then test points, test the intervals to see which ones are true to get ourselves solution sets. Okay, so for this equation f of x, we're going to solve first where f of x is equal to 0. Then we're going to solve the inequality where f of x is greater than 0, and then the inequality where f of x is less than 0. So there are 3 things we want to do. All right, so step 1, we're going to solve for f of x equal to 0. So that one's the equation. So let's take our equation, x squared minus 2x minus 15, and set it equal to 0. Let's see, that does seem factorable if I use a negative 5 with a positive 3. That's going to add up to negative 2 and multiply to negative 15. So that sounds factorable. So when we solve this, x minus 5 is equal to 0, or x plus 3 is equal to 0. So our solutions are x equals positive 5 if we add our 5 over, and x equals negative 3 from subtracting the 3 over. So the equation f of x equals 0 has the 2 solutions, x equals 5 and x equals negative 3. 2 solutions there. Now, let's say next we want to look for when f of x is greater than 0. We're going to solve this inequality. The very first thing that I would need to do to solve this inequality is find these 2 solution values. So fortunately, I've already done so. Then I'm going to put them on a number line. So let's they have to go in order on a number line, of course. So negative 3 has to be lower than 5. So those 2 values are on a number line. And then we partition that number line into 3 parts. And we're going to select values to test that are lower, between, and higher than our 2 solution values. So I can pick any number I want that is less than negative 3. I'm going to pick negative 10, just because I think it's going to be easy to plug that number into the equation. Any number that is in between negative 3 and 5, I'm going to pick 0, because once again, 0 is going to be easy to plug into the equation. And then any number bigger than 5, I like to go with 10, because I can plug that into the equation easily. Now, I want to know whether or not the output values, the y values, are greater than 0. So positive or negative. Are they truly greater than 0 positive, or no, they're not? So let's find out. Let's plug in 0 first. That's going to be the easy one. So 0 squared minus 2 times 0, that's all 0, minus 15. That one gives me negative 15. And I'm asking the question, is that greater than 0? And that is not greater than 0. So this is going to be false. So put an F for false, or write the word false up there. Now I'm going to plug in 10. So 10 squared, that's 100, minus 2 times 10, that's minus 20. So I've got 80, minus 15. 80 minus 15, that's going to be 65. and that is greater than 0, so that's true. We can absolutely plug this in on Desmos, it doesn't matter, but 10 was an easy number, so I could do it in my head. We're going to do the same thing for negative 10. Negative 10 squared is 100, minus 2 times negative 10, that's going to be 120, minus the 15, 120 minus 15 is going to be 105. That's definitely greater than 0, so again, that's true. Okay. All right. So my solution here is going to be the interval of values where this is true. And so I've got everything from negative infinity up until this value here of negative 3. And there's no equal bar on this inequality, so we're going to make sure that we put a parenthesis. We're not going to include the negative 3. We're going to exclude it, just go up to, but not including, parentheses there. And then we're going to start again here at 5. And we're going to go all the way up to infinity. So this is going to be the solution to the inequality where f of x is greater than 0. All right. And in the last case, I'm going to want to solve for where f of x is less than 0. I get to duplicate some of the work I did right here. I'm going to draw my number line, split up between negative 3 and 5. Those are the two solution values from that first equation right here again. I'm going to test those same numbers, negative 10, 0, and 10. And we come up with the same things. We come up with 105, but this time we want that to be less than 0. So 105 is not less than 0, so this one is false. It's a little messy, but that was the same number, 105 there. When I plug in 0, I still get negative 15. If I want that to be less than 0, it is, so that one's true. When I plug in 100, I got that 65, which is not less than 0, so that one's false. So it ran out of room right there to show the not less than 0, but you know that 65 is not less than 0, so false. The only area where the less than 0 inequality is going to be true is in the middle between negative 3 and 5. So that would make our solution here the interval between negative 3 and 5. So that's going to be our final answer for the f of x less than 0 inequality. Okay, let's take a look at the next page. We want to solve this inequality algebraically, state the solution in inequality and interval notation, and then graph it on a number line. All right. So first, I'm going to write down the related equation. The related equation is the same thing, but with an equal sign instead of the greater or less than. So this would be 3x to the third minus 5 equals 5x minus 3x squared. I need to solve that. That's the first step to solving any inequality, is to find the solutions to the equation, then test them and do the true-false for the number line. Because this is a polynomial, we better get it all equal to 0. So we'll have 3x cubed. We're going to add the 3x squared over to the left-hand side. We're going to subtract the 5x over to the left-hand side. And this negative 5 is already on the left-hand side, so it's now going to be equal to 0. Move those two terms over. Everything's on the left-hand side is equal to 0. Now we're going to attempt to solve this. There are 4 terms. We're going to factor, and we're going to attempt to factor this by grouping the first 2 terms and the last 2 terms. It's one of our strategies for 4 terms. GCF of 3 and x squared. If I factor that out, I would be left with x plus 1. And then minus GCF of negative 5 here, so minus 5, times, and then again x, negative 5 divided by negative 5 is positive 1. It looks like this worked in terms of the grouping method because the binomial x plus 1 is in common, so that can be factored out, and we're going to be left with the 3x squared minus 5, and we're equal to 0. All right, so we've got factored. I'm not able to factor this further because 5 and 3 aren't perfect squares, and that's fine. So we'll set each factor equal to 0. X plus 1 equals 0, and 3x squared minus 5 equals 0. The solution to the first part would be x equals negative 1 if you subtract that negative 1 over. The second part, we're going to add our 5, so 3x squared equals 5. We need to divide the 3, so x squared equals 5/3. And then we do need to take the square root of both sides. Don't forget the plus and minus whenever you take a square root of both sides. So I'm going to get two values here. X equals both positive and negative the square root of 5/3. All right. Now, to our number line, I need to put these three values in order: -1, positive square root of 5/3, and negative square root of 5/3. I know for sure the largest one is the positive square root of 5/3, but I'm not entirely sure how big the negative square root of 5/3 is. So let's just use the calculator to help us out. We could think about that value. Let's do the square root of the fraction 5/3. It's 1.29. So that means that -1 is going to be larger than the negative square root of 5/3, which is negative 1.29. Okay. That also helps me figure out that there's not very many numbers in between these two. They're going to be pretty close together. So let's work carefully to figure out some numbers on the far left, middle, and far right side here. If this is about -1.2, I can try any number. I'm going to go with something smaller than that. I'm going to say -5. Let's just say. You can pick whatever number you want. In between those, I've got to be really careful. Remember that the negative square root of 5/3 is -1.29. I have to be in between that and -1. So I'm going to pick -1.1. That's just a little bit smaller than -1 and a little bit bigger than the square root of -5/3. In between -1 and 5/3, I can pick 0. And then something bigger than 5/3, bigger than 1.21, I could pick 5, 10, 20, any number I want. Let's go ahead and pick 5. All right, I have a cube, so these numbers are going to get big. So I'm going to use Desmos to plug these in. I'm not going to do them by hand like I did in the last one. So let's go ahead and make a table. I also have two sides, a left side and a right side here. So I'm going to enter these into my calculator as both left and right side. So the left side, it's 3x1 to the third power minus 5. Just going to enter the equation that is there on the left side. And we're going to make another column over here and enter the right side, which is 5 times the x1 variable minus 3 times x1 squared. Now, you can get it equal to 0 and then do compared to 0. Some people like to do that. I like to use the original instead because just in case I made a mistake on something when I was subtracting these values over, I don't have to compare to 0. I can compare the two sides just in the original. I want to keep in mind that I want the left side to be larger. So we're checking to see when that left side is larger than our right side. Let's plug in our test point values. We're going to plug in -5. When I plug in -5, I get -380 larger than -100, and that is false. That is not true that -380 is a larger number. So we're going to say that one is false. I'm going to plug in the -1.1. It's going to give me -8.9 is larger than -9.1. That is true. We're going to plug in 0. 0 will give me -5 is greater than 0. That is not true. That's false. And then the last one, if we plug in +5, that gives me 370 is greater than -50. So that is true. We're true in between negative square root of 5/3 and -1, and we're true for values larger than 5/3. So the solution is going to be from negative the square root of 5/3, not including, because there's not an equal bar in the inequality, so I don't use a bracket, I have to use a parenthesis, negative the square root of 5/3 up until -1, and then from, let's take a break here, from positive the square root of 5/3 up forever, up to infinity. So this is going to be our solution in interval notation. Note at the bottom, just like with equations, we can also graphically solve polynomial inequalities in two ways. One of the ways for this one up here, let me rewrite this equation real quick, would be to look at the 3x cubed minus 5 greater than 5x minus 3x squared. So one of the ways would be to do an f of x for the left-hand side and a g of x for the right-hand side. And then on the graph, try to visually see where the left-hand side is bigger than the right-hand side. This is possible, but it's not maybe the best way to do this because I don't know where they're going to cross and how high it is. I know the x values, but I don't know their y coordinates or how hard it is going to be to see when they cross. So another way to do this would be to rewrite this. Is set to 0. So rewrite this as 3x to the third minus 5, and then let's just go ahead and subtract the 5x over and add the 3x squared over. You can put those terms in the correct descending order or not, that doesn't matter. And then compare this to 0. So I could graph the entire function as a function, f of x equals 3x cubed minus 5 minus 5x plus 3x squared. And then we're going to look on the graph for places where that function is greater than 0. The advantage to the second method is that instead of having to find some unknown height to compare, I'm comparing these to 0, which I know is going to be right on the x-axis. So it's going to be easier to tell where the function is above or below the x-axis than it would be to determine at some unknown height where I need to rescale my graph where one function is higher than the other. So I might have two equations and need to find out that this one is higher right here and over here. Like this is just an example. If I'm looking for when this function is higher, if that's f, it's higher here and here. But again, it's very hard to determine that. It's just my quick sketch right here. When I have some unknown height to work with, if that's f and that's g. Now, I don't know that that's the graph of these two functions. I just made up my own graph here to show this idea. So it might be something similar, it might not, but just to get the idea that I could use one of these two methods to solve. And this one is my preferred method because it's easy to see where 0 is on a graph, it's the x-axis, and I don't know what height these are going to be equal, so it's going to be harder for me to scroll out and find that location. All right. Let's minimize decimals here. We're going to look now at topic 2 on rational inequalities. This process is going to be pretty similar to polynomials. We are going to solve rational inequalities by finding particular intervals of input values. So we're going to consider critical values, which are going to be zeros, but also discontinuities. Not just places where the function's equal to 0, but also places where we're not continuous. That's going to be either our point discontinuities or our vertical asymptotes. Those are special places where the graph of the function could switch between being positive or negative. All right, so here's our function, f of x minus 2 over x plus 4. And we want to find where f of x is undefined, where it's equal to 0, where it's greater than 0, and where it's less than 0. All right, so undefined, this is a matter of finding the domain. So I'm just going to make a note of this right here. If it's asking me where f of x is undefined, that's another way of asking me what is the domain. Okay. So I'm going to take the denominator and set it to 0 to find out where it is undefined. For the domain, x is not equal to those values, so it's like the domain. I'm trying to find out where it is undefined. And so in this case, subtract the 4 over, x equals -4 is undefined. It's supposed to be an I, cursive there, is undefined. Or rather, f of -4 is what's undefined, right? -4 is the x value that makes the function value undefined. Now, if I wanted to know what kind of discontinuity that was, I would look at the numerator and I would realize that these don't reduce. So this is a vertical asymptote. I don't have to know that it's a vertical asymptote or a point discontinuity for this part of the question. It's just one of the two. So it's a discontinuity of some type. It's a place where the function's undefined. All right, so we've done that part. Now we are going to solve f of x equals 0. So we're going to take that function, x minus 2 over x plus 4, and set it equal to 0. Because it's a fraction, we're going to multiply both sides by the common denominator, which if there's only one denominator, it gets to be the common denominator. And that gives us x minus 2 equals anything times 0 is still 0. So I can solve this by adding the 2 over and get x equals 2. So the solution to f of x equals 0 here is going to be x equals 2. I also should have highlighted back up here at x equals -4, f of x is undefined. Okay, so I found the first two pieces, where f of x is undefined and where f of x is equal to 0. Before I can solve either of the inequalities, those two things need to be done. So let's now look at where f of x is greater than 0, and then we'll do less than 0 in a moment. We're going to make a number line, and on that number line, we're going to put the values both from the discontinuities and from the zeros. So both of these come into play. -4 is the smaller value, and +2 is the larger value. Sometimes I might dot this just to signify that I know it's an asymptote. And then this one is a solid point because it's my 0. There are different notations you can use so you can remember which one is which, or you can color code them. This one is from where the function was undefined, and this one is from where the function was equal to 0. Okay, now I need test points on the left, middle, and right side. So something that's smaller than -4, let me go with -10. Something in between them, I'm going to pick 0, and something bigger, I'm going to pick 10. I just picked 10 because it's easy to plug in. So -10 minus 2, that is -12, over -10 plus 4, that is -6. And I want to know, is this greater than 0? I'm testing right now in the equation f of x greater than 0. Two negatives make a positive, so this is +6/12. +6/12 is positive, so it is greater than 0. So this is going to be true. If I plug in 0, I have -2 over 4. 0 minus 2, 0 plus 4. Is this greater than 0? It's a negative number, so it is not greater than 0, so that's false. If I plug in 10, I've got 10 minus 2 is 8, over 10 plus 4 is 14. That's definitely positive. It's greater than 0, so that's going to be true. So our solutions are going to be on these sides here. From -infinity up until -4, not including negative 4. And then from 2 up into infinity, not including the 2, again, because there's no equal bar. Just a quick note about this. If instead, so that is my solution right here, for f of x greater than 0, if instead I was asked for f of x greater or equal to 0, how would that change it? So if I had an equal bar here underneath the inequality, all of this would be the same, but my interval would go from negative infinity up to negative 4. It's still not going to include the negative 4 because that was an undefined value, a domain exclusion. However, it would include 2, which is a solution value. So if I had an equal bar, I would have used a bracket on the negative 2 only. So never on a domain exclusion, only on a solution value, a 0. Okay, so just wanted to look at that in case it ever comes up. All right. We also need to answer when f of x is less than 0. We've already done most of the work for this. So we need to just redo our number line here. Negative 4 and 2 are still the values of interest. Negative 4 is from our domain exclusion, and 2 is from the 0. We're going to test the same values. We're going to test, different color here. We're going to test at negative 10, 0, and 10, just for ease here. This would have been negative 12 over negative 6 again. This time I want to know if that is less than 0. 2 negatives make that a positive. A positive number is not less than 0, so we would have gotten false. For 0, we would have gotten negative 2/4. And we want to know if this is less than 0. It's negative, so yes, it's less than 0. And then for our 8/14, we want to know if that's less than 0, and 8/14 is positive, so no, it's not less than 0, so that's false. So our solution value, if we were asked when it was less than 0, would be just in between those values. So our solution would be from negative 4 up until 2, and we're not including either one because there was no equal bar. So it's the interval from negative 4 to 2. Just in case, what if you did have an equal bar? How would that change it? If you did have an equal bar, everything would remain the same about this solution, but you're going to include the solution value for the 2. So the solution would have been from negative 4, not including, because negative 4 is a domain exclusion, up to 2, and you would include the 2 because it is a solution value. So the solution would look like this if it was less than or equal to 0 instead of just less than. All right, I believe we have one more example. So let's look at the last page here. Solve this inequality, state the exact solution, sets an interval notation. I see I've got a less than or equal sign, so we'll get a chance to use those parentheses and brackets appropriately here. Okay, we're going to get the denominators factored first. So I've got 2 as the numerator over. Looks like the first one factors as x minus 1 times x minus 3. Negative 1 plus negative 3 is negative 4, and negative 1 times negative 3 is positive 3, so that checks out. I am writing first the related equation. So I'm going to pretend right now that it's an equal side as we're solving this. And we're going to continue and factor on the other side here. The denominator is going to factor as a difference of squares, so x plus 3 times x minus 3. Okay, now that the denominators are factored, I'm going to be able to find the domain exclusions, so where f of x is undefined. So f of x is undefined for anytime any of the denominators is equal to 0. So for x minus 1 equals 0, or x minus 3 equals 0, or x plus 3 equals 0, or I don't actually need to say x minus 3 again since I already have it here. So we're undefined for x equals 1, x equals 3, and x equals negative 3. There's 3 values for which the function is undefined. We find that first, and then we solve our related equation. So I'm going to rewrite this. We've got our 2 over x minus 1, x minus 3 equals 5 over x plus 3, x minus 3. And we want to multiply both sides by the common denominator. The common denominator is going to have each of the denominators. So we're going to have x minus 1. We're going to have x minus 3. We're going to have x plus 3. I don't need another x minus 3 because they're going to share this one. So we're going to do this to both sides. Fortunately, there's only one fraction on each side, which is going to allow us to just cancel. We don't need any distributing. So the x minus 1s would reduce out here. The x minus 3s would reduce out here. And what I'm left with is the 2 from the numerator times this factor that doesn't reduce, the x plus 3. And on the other side, the x plus 3s would reduce, the x minus 3s would reduce, and I'm left with that 5 from the numerator times the x minus 1 factor that doesn't reduce. Let's distribute so that we can solve. This is 2x plus 6 equals 5x minus 5. We're going to subtract our x's over to the right just to give me a positive 3x over there. Add the 5 over, that gives me 11. So if I divide by 3, I get 11 thirds for the x value. All right, so we need to, on our number line, include all of the domain exclusions and all of the solution values in order. Let's make ourselves a number line. I know that negative 3 is the smallest value. Let's think about 11 thirds. 9 thirds is 3. So 11 thirds is bigger than 3. That's going to be the biggest value. So let's put 1 next, then 3, then 11 thirds. So they're in increasing order. They have to be in order on the number line. And now we're going to pick some numbers that are in between them. All right. So I need something smaller than negative 3. I'll pick negative 10. Something in between negative 3 and 1. That's where 0 is. In between 1 and 3, I'll pick 2. And in between 3 and 11 thirds. 4 is 12 thirds, so 4 isn't in between these. 11 thirds is 3 and 2 thirds. It's like 3.6. So if I pick something like 3.5, 3.5 should be less than 11 thirds. Okay. And then for the bigger thing, I can pick 4, 5, 6. Let me just go with 10. It's something definitely bigger than the 11 thirds. I prefer, when I'm plugging this into the calculator, to use the original in my table and to compare left side and right side. So let's clear this up. I'm going to scooch it over here and make myself a table. And then I can enter the first side as 2 over the x1 value squared minus 4 times the x1 value plus 3. I just need to enter x as x1 because I'm going to be plugging the numbers into x1 for the input. So we got our x1s to grab these values and plug them in. And I'm going to compare this with the right-hand side, which is 5 over x1 squared minus 9. Now I can plug in my test points, and I want to know, is the left-hand side less than the right-hand side? So we're looking for bigger on the right-hand side. We want to know if this is true or false for each of our test values. Okay, so on the first one, let's plug in our negative 10. When I plug in negative 10, I have 0.014. is that less than or equal to 0.05? That seems to be true. The right-hand side is the bigger in these two values. When I plug in 0, I've got 0.67. Is that less than or equal to negative 0.56? That's definitely false. When I plug in 2, negative 2 less than or equal to negative 1, that is true. When I plug in 3.5, I would have 1.6 less than or equal to 1.54. That is false. And then when I plug in positive 10, I have 0.03 less than or equal to 0.05, and this one is true. So for our solution values, we've got ourselves a true on the far left, a true in the middle, between 1 and 3, and a true on the far right side. So let's just make sure we're using the right values here. I also want to know which of these are solution values and which are asymptote values. Let's look back up here. We remember that 1 and 3 and negative 3 are all asymptote values. And the only one of these that is a solution value is the 11/3. So this is the only one that we're going to be able to be equal to. The other ones are domain exclusions. So this one will get a bracket, and these ones will get parentheses since f is undefined for those values. So my solution is going to go from negative infinity up to negative 3, not including negative 3. Then it's going to jump to 1, not including 1, up to 3, not including. And then it's going to jump to 11/3, but it is going to include 11/3 because we did have an equal bar in our inequality, and that is a solution value. And that one's going to go up to infinity. So these intervals, this set of these 3 intervals is going to be the solution here.